Hello, everybody. It's great to be here today. I'll be talking about Pravega, which is my newest project. I have been working on it with the whole engineering team of Pravega for roughly the past year. I am the engineering lead for Pravega. And today, I'll be sharing the stage with my colleague, Stephan, who's going to be covering the part of the Pravega work that integrates Pravega with Flink. So let's get going. As I was just mentioning, the talk has two parts. I'll cover the introduction. I'll talk about Pravega, explain the basic concepts, where we are with it, and then Stephan is going to come up here and talk about the connectors, the Flink plus Pravega part. So let's get into Pravega. Pravega today is an open source project. So I'm sharing with you the URL there in the case you're interested in going, checking the documentation, checking all the information we have there. There is a GitHub repository that, again, it's open. And you will find the GitHub reference in that web page, in addition to documentation and a lot of information about the project. That's the entry point of all the information we have about Pravega in the open source space today. Now, before I get into specifics of Pravega, let me say a few words about streams, or at least some intuition in the way I think about streams. We can start thinking about very basic pieces of data. Like I can get my name and my address, transform that into bits and bytes, feed that to a computer. That computer can process it, maybe store it in some database. But the interesting thing is that this is a fairly static piece of data. So it's my address. If I give it a slightly twist to this reasoning, and instead of looking at my address, I go and start looking at my location, then it starts making sense to think of the sequence of data that I'm generating. So all the bits and bytes that I'm getting out of those events. I'm in Barcelona, then I'm in Berlin, then I'm in Barcelona again. It makes sense to keep that sequence, to keep that order, in other information like time perhaps. So that we can make inferences about this data. It might make sense that if I'm in Barcelona, then in Berlin, maybe I traveled for a conference called Flink Forward. And so those kinds of inferences or value or results we extract out of data, we can only do if we keep this structure. We can have user data like this, but perhaps even more interesting from an engineering or infrastructure engineering perspective is if we start looking, in addition to end users, we start looking at machines. Computers that we are monitoring or sensors that are generating samples, room temperature, that kind of stuff. This is interesting because we have the potential of producing a lot more machines than the number of people on the planet. We're not necessarily going to do it. We don't know how we're going to end with this, but we do have that potential. And as we know, at least computer machines are able to generate data at a much higher rate than we can. And so this is a very challenging problem. All infrastructure we come up with need to be able to cope with this volume of data. Now, what about processing these data streams? So what I'm going to cover next is not necessarily new. Actually, it's not new at all. So the architecture we have been using recently to process those data streams are fairly well known. People have been using this in production. At a very high level, we can think of that of such data pipelines, such stream pipelines as a black box as we get, we get some streams in and we crunch the data, get some streams out, or store that in some additional data store for further processing. But when we look inside the box in slightly more detail, one thing that is happening is that ingest, that stream is being ingested into some form of messaging substrate, some messaging system, which is decoupling the stream processor from the source. That's useful in a number of ways. We don't want to overwhelm the source, so we don't want to overwhelm the data processor. We don't want the source blocked waiting for the data processor to finish. So we put that substrate there to buffer the data for us and offer that decoupling. And you can have multiple stages. In fact, it doesn't even have to be linear. You can have branches and have parallel stuff going on there. But the important point is about this messaging system that is ingesting the data for you. A couple of important limitations that we observed with the current systems are, first, that the data stored there is not supposed to be stored permanently. They buffer the data for maybe hours or days, but you're not supposed to keep the data there for months or even a year. The systems are not designed to do that. Now, as a consequence of that, the system does not expect to store data for very long, and as such, is not designed to accommodate storing an unbounded amount of stream data. So if you have a stream that has been going on or running for a very long time, and you want to keep all that data, then you won't be able to do in that messaging system, in that messaging substrate. And so one of the things you might end up doing is just pulling the data out of your pipeline and storing in some other form of bulk store. And so in addition to that pipeline, if you want to preserve that data, then you have to put the data in store somewhere else. So with those limitations in mind, this is what we were trying to achieve with Pravega. So the target of Pravega is to be a stream store where we are able to store data permanently. Well, if you choose to, obviously, we're not going to prevent you from deleting the data if that's what you want. But in principle, if you want to preserve the data for an unbounded amount of time, an unlimited amount of time, you can. We want to store that in the form of a stream. As you are generating it and you are ingesting it, we want to preserve that order of events, that order of bytes for you. And finally, because streams can be long-running, you might have an unbounded amount of data, and you want to be able to store that. So that's, at a high level, these are the things that Pravega is trying to provide. So now, streams in Pravega. So Pravega enables you to create streams where you can append to the streams and read from the streams. So at very basic terms, this is what it offers. But if that's only what it offers, then I might end up in trouble, because if I have one sequence of bytes per source, that might not accommodate the rate of ingestion that I need. And so as other systems have done, if we start thinking about parallelism, what kind of parallelism that we can provide, we enable streams to have multiple segments. So you can write in parallel to those segments. Segments are sequences of bytes. And to decide when you're getting events from the source and writing to Pravega, to decide which segment you write to, you use a routing key. Now, one interesting fact about the segments in Pravega is that they can be sealed. If I seal a segment, it means that I cannot append to that any longer. Once sealed, you cannot append to the segment any longer. Now, knowing that I can have open segments that I write to and segments that can be sealed, one very good way of interpreting what Pravega does is that it stores segments. It's primarily a segment store, where the segments it stores are either open or sealed. But wait, you're telling me that segments can be sealed, but how is that even useful? Why would I even care about segments being sealed? Sealing segments, it's useful in a number of ways. One being that I can take two sealed segments, append an open segment, and have a stream. The point I made earlier about having an unbounded amount of data on a stream comes from this ambiguity. Because if you think that each one of those segments can live in a separate server, the amount of data I can have on a single stream is given by the capacity of all the servers in the system in the extreme case. And so architecturally, I can have as many segments using all the capacity of all the servers in a cluster. But that's not the only way. I talked about parallelism a few slides back. So another thing I can do is I can take 2 CO segments, put them in parallel, and append 1 open segment, meaning that at some point I had 2 segments in a stream, and then it became just 1 segment. But this is still a bit abstract. Let's talk about a couple of very concrete ways of using this ability of composing segments, sealing segments, and so on. One is scaling a stream. Say that I have a stream that starts with one segment. So I'm appending to that segment. And at a later time, I decide that that 1 segment is taking too much load. OK? Then what I can do is I can seal that segment, create 2 new segments, 2 new open segments, and append those. And so what that means is I transform a stream into a 1-segment stream into a segment into a stream with 2 segments, which gives me more parallelism. In fact, going a bit deeper into this thought, this is what we expect. This diagram illustrates what we expect a stream in Pravega to be. So we can have a stream that starts with a segment. At some later time, the system decides that that segment is taking too much load. So we split that segment into two segments 2 and 3. Then at some later time, T1, we decide that one of the segments, it's still hot, and so we need to split it further. We split it into 4 and 5. And at some later time, we decide that 4 and 5 are doing OK. They're not taking as much load, so we merge it back. So this is possible with Pravega. Now, one interesting observation, if you haven't realized that by yourself yet, is that I was talking about routing keys before, and what this diagram is showing me is routing key space versus time. And as I am reconfiguring that stream with respect to segments, the key ranges that I have, the key ranges of the stream are not statically assigned to segments. So it's dynamically changing as we create new segments or as we scale the segments of this stream. This is more of what we expect it to be in a real production environment. This is not a production graph. This is from a virtual cluster where we run some experiments for a period of roughly 2 hours, and we can see the dynamics of the stream. So we can see it's splitting and merging in a number of places. Looking at the colors, what this is saying is if a segment has color light blue, it means that the load is light. If it's going towards red, then the load is increasing. Bright red is very high load, and the white represents the separation of the segments. Now, to take a couple of examples, so if you look at the top, we see an example of a scale down event. We have 2 segments. They, so the load is not very high, so it's all blue. So the system decides that it's okay to merge it. So you see a scale down event there. Here at the bottom, you see an example of a scale up event. So the load is high, right? So you see a lot of red in that segment. We split up into 2 segments. So we scale up. Now, let me move on and talk about a second example of where this composition, or where sealing and composition of segments makes sense. Say I want to do transactional writes, which is a feature that we offer in Pravega. We have a stream that we want transactionally to, and that has 2 segments at the time I have the transaction. When I begin the transaction, I create transaction segments. So instead of writing directly into the stream segments, I create transaction segments and I write to it. So at steps 3 and 4, we can see that the transaction writes go into the transaction segments. Now, when I decide to commit, what I do is I seal those segments, and I merge them back into the parent segments or the main segments of the stream. And you might be wondering, so why do I want to do that? Why didn't I write directly into the stream segments? So we don't do that because transactions can abort. And if I abort, the only thing I need to do is to delete those transaction segments. I have no thresh or no unused bytes in those segments. And so again, this ability of freely creating segments, sealing them, and managing the stream in this way enables us to do things like this and be efficient with respect to transactions. But one question you might ask is, I'm talking about this segment manipulation. Is this something that the end user or the developer needs to do? So not at the moment. Nothing prevents us from actually doing this in the future, but today, this is all done by our control plane, implementing the form of a controller, which has a few important tasks. The two high-level ones are stream lifecycle, so creating, deleting, scaling a stream. So all tasks that are performed by the controller. Some of these things can be done manually. For example, we can manually scale a stream. And the second being transaction management, creating a transaction and completing a transaction by either committing or aborting. Let's move on and talk a bit about the API and the semantics of our API. Pravega internally understands bytes. I've been talking about events, and in fact, our API exposes events, but internally, it's all about bytes. Considering an initial API that covers events makes a lot of sense because it covers a lot of applications. A lot of applications naturally map their abstraction to events. And so it's all good. But in the future, we might consider exposing other things. So for example, we could have a byte-oriented API. So currently, in this event API, event-driven API, we don't interpret the bytes. That's entirely up to the application. All we require from the application is a serializer so that we are able to deserialize the events that are given to Pravega. Because we have this notion of we are promoting this notion of a storage system for streams, the abstraction we capture is the one of a reader and of a writer. So here we have a stream writer, or I'm illustrating how you would use a stream writer. So we have a client factory. With that, you create a stream writer, and with that stream writer, you can just go into your own loop and start writing out whatever events is part of your source. On the reading side, we also use the notion of groups that has been used in other systems, and so when we create a reader, we associate it to a reader group, and we go into the loop of just reading events out of a set of streams, the set of streams that are associated with the reader group. It's also worth mentioning briefly how transactions work. Is not very different from the main event writer. So you begin a transaction, you write, and when you're ready, you commit it or abort it, depending on the logic of the application. Now let's talk a bit about the semantics of the operations. On the write path, what happens is the event writer, when he wants to write some events, he needs to get the information of where the segment is going to write to or is going to append to lives. And he's going to get that from the controller. So it goes to the controller, asks where that segment lives, and starts appending to the segment. Or if there are multiple segments in the stream, it's going to do that for each one of the segments. Then in the segment store, it's going to write synchronously into tier 1, which today is implemented by Apache Bookkeeper. And asynchronously, we're going to flush that data into a secondary storage, which is our long-term storage. And once that happens, we we can trim the data out of tier 1. Now, the reasoning for this architecture is the following. We needed a durable low latency write path for the events that we are appending. And so Apache Bookkeeper is really good for that. So it provides durable low latency writes. But we felt that we needed, for reading, we needed a solution that provided high throughput in the case that we are doing catch-up reads or we're doing archival reads. So later on, you want to come and capture or get the data for reprocessing out of Pravega. For that storage, so tier 2, actually both, tier 2 has a few options. We have made in a way that you can implement different bindings. We have implemented ourselves three different options, one for HDFS, one for NFS, and another for what we call extended S3. Extended S3 is because one of the products we couple with exposes that interface. But others can be written here. We're not limited to those three options only. So that's a very important point. On the guarantees on the write path, the writer appends in the order it receives from the application. It uses a writer ID to determine, to spot duplicates in the case of reconnection. So if it disconnects and reconnects back as part of the setup of the connection, it determines where it has stopped. Now, that doesn't cover the possibility of the writer crashing. So to deal with writers crashing, we need to use transactions. So with a transaction, if the writer dies, then it needs to, so the transaction will just time out and abort automatically. But let's go over a bit more of the detail on these 2 points with a couple of illustrations. So for reconnects, say I have a writer with ID 10. He wants to write black, blue, and red. He writes black. On the segment store side, we remember with the writer ID the position that has been written. So when he writes blue, he never receives the ACK. Connection breaks. When he reconnects as part of the setup, he learns what was the last position that he has written. In fact, the blue one has gone through. And then he knows that he has to resume from red. But the point I was trying to make before is that the writer ID is not really remembered by, it's remembered by the segment store, but not by the writer itself. And we don't force the application to do it. So to deal with the writer crashing, we use transactions. The writer starts a transaction against a controller, then it starts writing events. So it writes black, but then it crashes while it's writing blue. Controller is going to time out that transaction eventually, and it's going to abort it. If the application remembers a transaction ID, the application can do it itself, but it's not strictly necessary. The controller can abort it for you. And then what the application would do is start a new writer, which would have a different ID, and start a new transaction and start writing those events again. Obviously, this makes the assumption that you're able to get those same events back. So your source is able to keep those events long enough that you can get them back for rewriting. Now let's talk about the read path. So on the read path, you also need to get from the controller where the segment that you're going to read from lives. And you go to the segment store, request bytes. If those bytes are there in memory, so if it's a tail read, then you just read those bytes. If not, then we pull the data out of tier 2 and feed it into the reader. So tier 2 in this case plays a very important role because if it's a catch-up read, then we can serve those reads with very high throughput as a property of the tier 2 options that we are considering. Readers live in a group. Each reader group has a set of strings associated to them that they read from. We assign segments from that set of segments to the readers of the group. And we do that coordination of assignment through a facility that we call the state synchronizer. The state synchronizer is something that we use internally for that coordination, but we also expose via our API. It works by using a Pravega stream and writing conditionally into not a Pravega stream, a Pravega segment, and making sure that the writes correspond to and write conditionally. So the writes only succeed if the state of the segment is what the write expects. Essentially, we are doing a compare and swap style of operation here to make sure this works. And if you're into the whole consensus stuff, this means that we can implement replicated state machines with this. And so it's not only, again, limited to the reader group. You can use that yourself if you want. But this is to show that we use it internally as well. And as part of the reader group, there's a very important feature because that's what allows the readers to coordinate what they're doing with respect to the streams they're reading. But I'm not going to cover this any further. This is a topic for further discussion for another time. But if you're interested in it, we can talk about this after the talk. But let me illustrate the work of reader groups plus scaling, because that's an interesting interaction. Say I have two readers, each one is reading from one segment. Then at some time later, segment one is split into two new segments. I was taking too much load, system decides that it needs to scale up. So we split that into two segments. Now, that first reader eventually is going to hit the end of segment one. And when it does, it's going to pick from the controller the successors of that segment, which are segments 3 and 4. And the next thing it's going to do is pick a new segment because it has no segments to read. And so it picks one, it picks segment 3 to read from. The second reader is still reading from segment 2. When it ends, it decides that it doesn't, it's not taking enough load, it can pick another segment. So there is one available, which is segment 4. And the final assignment that we get is reader 3, 2, and 4. Now, this assignment is not unique. I'm not presenting this to you saying that this is the only way this can happen. The main thing I wanted to illustrate is that because reader 1 hit the end of segment 1, doesn't mean that it's going to pick the successors. You get the successors, updates the state of the reader group via the synchronizer, and so those segments become available for assignment, and that assignment can be to any of the available readers. The next point I want to cover is about checkpoints, and this is particularly important because Flink makes use of these objects. So the checkpoint object essentially gives you a mapping of segments to offsets. This is opaque to the application, but internally, this is what it's doing. And to get an idea of how it works, again, I have my reader group with 2 readers. Then I need some external process to initiate a checkpoint. So if you have a master in your application, then you can invoke this initiate checkpoint call, give it a name, and bootstrap the process. So what's going to happen is there will be some coordination, again, via the state synchronizer. The readers are going to receive a checkpoint event. So that checkpoint event indicates to the reader, to the application, that whatever is part of the checkpoint needs to happen at that moment. So if you need to flush data downstream, or if you need to save some local state, that's the time to do it. Once those events are delivered, we collect all those offsets, we wrap up that mapping, and return that checkpoint object. We can reset to a checkpoint. If we give that checkpoint object, it's going to start the resetting. The readers, we need to reinitialize the readers. Once we do that, then they will receive a new assignment according to the new state of the reader group. And this assignment can, in fact, be different from what we had before. So here, I changed the assignment on purpose to illustrate that this is a possibility. OK, so to wrap up this part, takeaway messages about Pravega. So Pravega is all about unbounded stream data. So I try to argue that we have an architecture that enables you to store an unbounded amount of data for a stream if that's what you choose to do. It can be permanently stored. We architecturally do not have anything that prevents you from having a retention policy that is even years long if that's what you want. We provide the ability of growing and shrinking the size of a stream as we split segments and create new segments, or as we merge segments and reduce the number of segments. So we make streams elastic. And because we have this ability of growing and shrinking the number of segments of a stream and reconfiguring it dynamically, we can scale producers and consumers independently. So if I add more producers, that's going to induce a change in the number of segments of my stream, which is going to give me more capacity for writing. And on the reader side, you can scale that if you want, but it's entirely up to the application to do it. So Pravega is under active development. As I mentioned in the beginning, this is an open source project, so all the work we are doing is happening on GitHub right now. And we're looking at our first use cases. As for ongoing work, there are many things that are happening. So a few things to mention is we are doing performance tuning, adding scaling support so that we can scale applications downstream, event time support, geo-distribution security, which is far from being a comprehensive list of things that we are working on. There's much more that's ongoing, and so it's an exciting times for the project. We are trying to get a community to work with us around this project. Again, information on the Pravega.io website. And if you're interested in contributing and working with us, we're more than happy to have new contributors and working with a community. All right, and with that, I will pass the word to Stephan. Thanks.
Okay. Yeah. Thanks, Flavio, for the really awesome introduction to Pravega. I'm going to just add a few words on how we're making Pravega and Flink work together. So, I mean, the idea is that we built a combination of the two, a deeply integrated combination where Pravega is actually the streaming storage, the messaging substrate, the pub subsystem that connects a lot of streaming applications, and so we're not only thinking of Pravega as something that could be a streaming source for Flink, but also a sink, so that you can actually build like longer pipelines of streaming applications that are connected via Pravega. And so I quickly want to talk about how exactly we're implementing the source and the sink side of Pravega, because kind of the unique properties of that system make these look a little different than your average source and sink and Flink, which I find quite interesting. So first, how do we do the reading from Pravega? So like a quick recap, if you have a Flink streaming job, you have a few readers that start reading from certain Pravega nodes. Each node has certain segments, and the readers have actually grabbed certain segments that they read from. The assignment, as Flavio mentioned, is actually managed by the reader group, by the controller. In some sense, that's the same thing for example, in Kafka, but Flink completely circumvents that mechanism and says, we're not leaving the reader group in charge, but we're directly controlling the segment assignment ourselves, because that way we can get a consistent view where everybody is, in which segment. We can checkpoint that in the sources. Now, what we actually decided to do in Pravega is not go that route, so not circumvent the reader group, but leave the reader group in charge of everything. And that is really important, because if we would actually try to circumvent it again and directly go to the segment level interface, which is not exposed, but I mean one could expose it, we would actually kill half of the cool features that Pravega has, like the dynamic load balancing, the dynamic scaling, and so on. So in order to actually use those, leaving the reader group properly in charge is actually key. And then the challenge is, how do you actually do a consistent checkpoint if there's a reader group in charge that is, at any point in time able to withdraw a segment from you, give it to somebody else? There's like each reader individually cannot really get a consistent view of what is happening. So just one example could be that, look at the left side here. We're in this situation. Segment D has just been sealed, has finished, and has been split into segment E and F. And some reader, the second one, has actually grabbed segment F, but segment E has not yet been, claimed. So if we would just take a checkpoint in the sources, like we, for example, do in Kinesis or in Kafka, we'd actually just lose the information of checkpoint E. We wouldn't know anything about it. Are we at the beginning of it? Have we actually completed it? Like, would not be a well-defined, well-defined state. So the way it actually works is slightly different, and that's kind of interesting because it's the first system that works like that. If we're taking the job manager and the checkpoint coordinator here, whenever we start a checkpoint together with this source, what actually happens is that there's a hook in on the master side of the job manager, which actually calls into the Pravega controller API, into the reader group API, and says, okay, here's what we need to do. We need to initialize a checkpoint, and you can think about it like that. These would be the positions in each segment as they are observed by the different readers, and actually Pravega determines them at this point in time or the readers as they are connected there determine these positions. And then the checkpoint data for the source, like where is each source or each reader in each segment currently, is actually returned by the Pravega reader group API. It's not actually determined by the sources themselves. And then the sources actually get a notification. This is the point that corresponds to the checkpoint that was just triggered and for which the information was returned. So the exact mechanism is like under the hood, how Pravega does it. Actually, I learned about this only recently as well. But conceptually, you can think of it like that. It works like you can think of it like Pravega injects the checkpoint barriers into the initial stream. They're actually not injected by the Flink sources, but they're injected by Pravega or by its reader group API. It determines the point where each reader currently is, because it has the view of all the situation of each segments, which segments are allocated where and which are not allocated to any reader at any point in time. So and from then on, it actually completes, pretty straightforward. The barriers flow through the streams in Flink. The operators take their snapshots, and the checkpoint from the source offsets is actually written as part of the checkpoint metadata that the job manager persists. And we added a new mechanism in Flink for that, which is master side checkpoint hooks. That that the Pravega source declares that get instantiated on the job manager in the checkpoint coordinator. I think it's a very interesting mechanism. We can. Oh. Okay, here we go. Sorry. So it's the first system that uses that, but you can think of it as I think it's a very interesting mechanism that has potential applications in other sources as well. Writing to Pravega. So there's multiple writers to Pravega currently. There's one that has basically at least one semantics. So on a checkpoint, you do make sure that all data is not buffered in any writer anymore, but it's actually going out, and it has actually reached a persistent state in Pravega. But the way more interesting one to talk about is actually the exactly once writer, which uses these transactions that Pravega offers. So a bit different to maybe some of the other systems as well is, again, on the writer side, you're not in charge of really declaring which partition you write to, because partitions don't exist, just dynamically created and sealed and merged segments. So what you actually declare instead is always a routing key. So in the producer side, you always declare a key that you want to associate this event with, and then this key determines where the event goes. And order is actually guaranteed by key, not by partition, because that concept doesn't exist. But if you actually look at most use cases, what you do want to do is guarantee an order by key. So you route by keys to partitions and then use the partition order as a key order. But you're actually imposing more order than you need. So here you would actually directly define your order by a key. To look at how do the transactions work, if you think of a checkpoint in Flink, it's something where many parties are involved, many operators and many parallel syncs. So whether actually a checkpoint goes through or does not go through is in the end not the decision, or it involves multiple parties that have to agree on the fact that this checkpoint is okay. Like each operator has to say, okay, I've actually reached the checkpoint, I didn't crash in the meantime, so from my side, that checkpoint is okay. And so if you actually integrate this with with something like transactional writes, you do end up with something that is comparable to a distributed two-phase commit protocol. Now, I really want to say that this is actually, it's not like your average two-phase event write with insanely long voting delays and so on, but it's like it's again like in Flink, elements are flowing, and while they're flowing, the next piece of work can happen. So it's actually it is actually like the voting delays, for example, for Flink checkpoints, whether they happen or not, whether the job manager gathers all votes, processing continues at the same time. So you're not actually seeing these delays here. So the basic algorithm for this is the following. Like for each checkpoint, you open a transaction. Between checkpoints, you write to these transactions. And whenever you do a snapshot in an operator, you basically vote to commit that transaction. You make sure that everything in that transaction is, from Pravega's side, ready to commit, but you don't commit it yet. Then you open a new connection and you put this, let's say, this transaction to the side for now. And when the checkpoint is actually fully committed, when the job manager says, "Okay, I'm actually flipping the switch and say this is for me now the latest checkpoint," then you use that to commit. And if you actually have for example, a crash between the point when the job manager commits and the commits actually go through to Pravega, there's strategies to detect that and retry the commits. And commits are idempotent, so even if you actually commit them multiple times, the data only ends up once. So let's do a quick illustration how that actually looks like. So let's say we're writing a bunch of data as part of a transaction. Then comes checkpoint 1. This is in the sync operator. We open a new transaction. The next event goes to the new transaction. Let's say the job manager now acknowledges that this checkpoint has gone through. The notification that checkpoint has gone through actually arrives in the syncs. And then the syncs commit their data. And then more data goes in the transaction. The next checkpoint arrives at the sync. We're opening again a new transaction, committing this. There may even be another event coming that is written to the transaction 3. Then the notification that checkpoint 2 commits arrives at the sync, and the data actually arrives in Pravega. Then we have a few more events here and then a crash, but then everything is okay, right? We're falling back to checkpoint number 2. For recovery, and we didn't have any data that was past checkpoint number 2 in Pravega yet, so we're exactly once, we're okay. There are a few other cases. For example, the beginning, let's say, is exactly the same again. We have transaction 1 going through, transaction 2 happening in the sync. Transaction 2 has happened on the sync, so the sync has actually, made sure that the transaction as done with Pravega is okay for now, but it hasn't committed it yet. And then before transaction 2 is actually acknowledged by the job manager, the whole thing encounters a failure. So in fact, transaction 2 checkpoint 2 never completes. That is, for example, the case if that sync completes checkpoint 2, but that sync does not complete checkpoint 2, right? So we're actually okay here. We've actually put all data into the transaction, not yet committed, and before this one can actually say, "Hey, from my side, checkpoint 2 is okay as well." You would have a crash and you would go to checkpoint 1. So in that case, it's actually okay. No data from checkpoint 2 ended up in Pravega as well. The fallback would be checkpoint 1 because it's the latest globally acknowledged checkpoint, and we're good. The most tricky corner case is, if you wish, if we actually go through a similar situation. Checkpoint 2 is acknowledged on the node. We're starting another one. It's actually acknowledged globally. The job manager acknowledges it, but before that message comes back and the commit to Pravega can happen, we actually see a crash. Now at that point in time, our fallback is actually checkpoint 2, but we have not yet put the checkpoint 2 data into Pravega yet. So if we actually see what the situation after Flink recovery would look like, is somewhat like that. Checkpoint 1 data is in Pravega, checkpoint 2 data is in a pending transaction, and we're going back to checkpoint 2. So what we do on recovery, we recover the transaction handle. The transaction handle for each pending transaction is always stored in the checkpoint. It's a few bytes. Think of it as a UUID. And on recovery, the transaction handles are always recovered. It actually checks what is the status of the current transaction, and if it's not committed or if it's not sure, then it will actually send a call to commit it. In which case, the data is committed, and then it goes on. So that is roughly how on the producer side the integration works, and it's actually quite a pretty implementation. Just thanks to this very nice transaction API on Pravega side. Okay, with that, we're pretty much at the end of the talk. There are a few things that we're actually looking to do next in this integration. The first thing is, Flavio mentioned that Pravega has this really nice implementation of dynamic scaling, where it scales segments, and there's the number of segments depending on the data load usually means that you should probably follow the number of readers in a very similar way. So reacting to these like scaling in and scaling out hooks on Pravega side to actually make Flink scale in the same way is one of the next things. And another thing that is, it's more like a thought right now. This very nice concept of state synchronizers that Pravega offers is actually something that, you know, allows you to do a lot of the functionality that Flink currently does directly through Zookeeper for high availability, like leader election, agreeing on what is the latest completed checkpoint, and all of these things. So actually just using Pravega as our high availability service for distributed consensus is something that we're also looking at. I think we're way over time. We'd have to take questions afterwards, but I hope you liked the talk. And yeah, if you want to learn more about this, just ping Flavio or me. Thanks.